How's it, guys? Welcome back again to Math 135, nearing the end of our semester here. One of the last sections, third to last. Yeah, we had 3.2, 3.3, and 3.4. Okay, today we're talking about logarithm functions. Awesome. You know, when I first learned about logarithm functions, I found them really befuddling and bewildering. But, you know, after spending a little bit of time with them, they're really not so bad. So don't be intimidated. It's going to be okay. Number one topic today is to define and evaluate logarithm functions. Pretty straightforward. Number two, find the domain and range. And that's also pretty easy. And then number three, graph them. We're going to use the same kind of transformations we did with the exponential functions and also, you know, just function in general. And the last thing is find the inverse of functions, either involving exponentials or logs. And just kind of a spoiler, but it's right here in the top paragraph. But logarithm function is the inverse of the exponential function. Actually, we're gonna do that right now when we talk about the definition. So here's the definition and how we evaluate logarithm functions. First of all, what is a logarithm function? It's a function of this form. Logarithm, we say log for short, yeah? So f of x equals log base a. And the base, you know, the easy way to remember it's a base is in the base of the function itself. See how it's kind of like at the base of it or the bottom of it, right? And then this is the base a of x. So log base a of x. Now this is only defined when a is bigger than 0 and not equal to 1. It cannot be equal to 0. It cannot be negative. And the reason for that is going to be apparent as soon as we look at this next definition. So here's the definition. I'll come back to the domain and range in a second. Definition says that the log y equals to log base a of x if and only if, so this is telling you, this is basically the definition, if a to the y is equal to x. So looking at this thing, this is the base of like the exponent, right? If I take this to the y power and it results in x, then that means when I try to evaluate my logarithm function, log of base a of x, then that y that was the exponent is the result. I know that kind of sounds confusing, right? But really, the way to think about this is just directly related to the exponent. So if the y is the exponent that I wanted, and I take the a to the exponent and gives me x, then that means that's what the overall log base a of x is. Okay, you know, I think that's kind of one of those things, maybe pause, think about it until it starts to click in your mind what's going on here and how you might go back and forth. And then, yeah, so pause the video if you need to, just let it kind of sink in for a second. Okay, now let's go back to the domain. So the domain says it's from 0 to infinity, right? Well, why can't you be 0, first of all? Well, think about it. If I plug in something as 0 here, that means I have to take some element a, right? Raise it to a power and get me 0. But how could I possibly take anything to a power and it result in me getting 0? It's not possible, right? If I put in a big negative number, I can get really small. I can get a very small number, but it's impossible to actually reach 0. And so right there, it's not possible. Here, if I think about it there, let me do this. Sorry, my thing was getting stuck here. Let me just remind you real quick of the exponential function, how it looks. And we talked about this last time, right? Remember the exponential function from last class? It's got one of two forms, right? If you have a base that is bigger than 1, then it looks something like this, right? And so you ask yourself, okay, what power or what x down here would give me 0? And looking at it, there's nothing, right? Because the horizontal asymptote is at 0, so it never touches 0. And looking at this same picture, what value of x would give me negative value? And the answer is nothing again, because this graph we know from before is always above the x-axis, right? Strictly above. So there's no way that I could reach 0, no way I could reach a negative. For that reason, for the domain of the log function is from 0 to infinity. And that same thing is true even if you have a fraction as the base of an exponent function, right? This is the exponential function from last time. Because that guy looks like this, and it also never touches 0. Okay, so always domain is a 0 to infinity. Now the range is negative infinity to infinity. Now let me give you a picture of what a logarithmic function looks like now. So here's a logarithmic, typical log function. If this base down here, it's bigger than 1, then your log function looks something like this. Let me think. Where should it cross? When y is 1, right? Or sorry, when y is 0, I mean. When y is 0, this x is going to be 1. Why is that? Well, because a to the 0 is equal to 1, right? So you know how with the exponential function you had 0, 1 as a point? This is going to switch around the other way where you have 1, 0 as a point. So when y is 0, x is going to be 1, right? So the graph looks something like this. It gets really steep as it approaches the vertical axis here. Never touches. And then it continues to grow. But it kind of grows slowly. That's a typical log function, right? This is when a is bigger than 1. And that's what this says here. It says it's strictly increasing from 0 to infinity for a bigger than 1. Notice that this doesn't cross past this y-axis, right? So you don't go past 0. But you do go negative forever. You do go positive forever. So for that reason, you see the range goes from negative infinity all the way to positive infinity. Okay, what about when a is between 0 and 1? So remember you said a cannot be 0, cannot be negative, but it could be a fraction. It could be a small fraction. What happens then? Well, then it's going to be decreasing. Now, we're still going to get that same point 1, 0 though, because even if you have a fraction, if you raise a fraction to the 0 power, you're going to get 1, right? But what happens there, it just basically looks similar, but it's sort of flipped around, right? Like this. So like that. So it gets really steep again towards that vertical axis, right? You got a vertical asymptote right there. And then it's going to get upwards forever and downwards forever. So you're going to get all possible values, negative infinity to positive infinity, but just in reverse order. Okay, think about what the exponential function looked like for a fraction. You guys remember that one? It looks something like crossing through this point here, right? 0, 1, and then decreasing. So in that case, it looks something like this, and approaching the x-axis that way, right? But check this out, guys. Look, if I draw the line y equals to x, you see how it crosses and it's a reflection of itself. So that fits with the idea that these guys are inverses, and they could do the same thing for the positive values as well. Okay, so recapping, what did we learn? We learned, okay, logarithmic functions has this format, right? Fx equals to log base a of x. Not define when a is bigger than 0. I'm sorry. Only define when a is bigger than 0. A cannot be 1 either. Oh, I didn't talk about why a couldn't be 1 yet. Why can't a be 1? Well, if a was 1, if I raise a to any power, no matter what power I raise it to, it's always going to give me 1, right? 1 to any power is just going to be 1. So when I try to input a 1, what happens? Let's say I have x like 5. I want to get 5. Well, a to what power is going to give me 5? There's no possibility. There's no possible answer. That's why a cannot be equal to 1 either. Kind of similar reasoning for why a cannot be 0, yeah? Okay, a is a base. A is a base, we said that. I already said why this is. Remember that? Okay, what else do we need? Yeah, okay, so the definition log, this is just recapping, yeah. We said y is equal to log base a of x if and only if a to the y is equal to x. Now, I'll get to the graph later on. Okay. Strictly increasing. So it's strictly increasing like we saw in the graph for a bigger than 1. If a is a fraction, then it's strictly decreasing like we saw in those quick graphs. Okay, one more thing to talk about. Okay, so last thing to talk about is the common logs. A equal to 10 is called the common base. And think of it as if 10 is the base, then you'd have log base 10 of x, right? Well, in the case of the common base, there's a shorthand notation, and that's simply to just not write anything. You just write log of x. So anytime you see just log x, and you're like, oh, what's the base? It's missing. Then that just means it's actually assumed to be the common base. So this is called the common log. If you don't have it explicitly notated, then we're assuming that the base is 10. Okay, there's another very popular logarithm, and this goes along with that very important exponential that we learned last time, which is when the base is e. So if the base is e, if a is equal to e, remember you saw e was a number, it's approximately 2.7182, and that goes on forever. This is called the natural base. That would make it log base e of x, right? But shorthand notation for log base e of x is ln. How did you get ln? What's the natural log? I guess the n part stands for natural, and L still stands for log. So really that's log natural, but I don't know, I guess that doesn't look right. NL doesn't look right, so they just left it as ln. I don't know, I'm just making stuff up. I think that's why, but anyways, this is called the natural log. This is no notation that they use for that. Okay, and it says to try questions 1 through 8, but before we do that, I actually have a little bit of additional notes down here. It says, just a reminder about the definition of exponential functions. I guess I should have talked about this earlier. So logarithms and exponentials are inverses. That means they undo each other. Hold on a second. I feel like it's in the wrong spot, actually. Do I want to talk about inverses yet? I think I'm going to save this for later, actually. Yeah. Let me save that for later. Yeah, sorry guys. That was I think I meant to put this notes over here. I meant to put that down here. So now my notes are kind of screwed up, but it's supposed to go down here with when we talk about the inverses. So I'm going to switch my notes around. Okay, anyways, let's get into the questions. Okay, super easy. Find the indicated value, log base 2 of 64, blah, 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 blah. Okay, let me copy these questions. Right now for these guys, we're not using a calculator yet. Although later on in next section, you'll learn a cheat way to just do all these with a calculator. And if it's not the common log or the natural log, you got to use a little trick if you're trying to use a calculator. But for now, I'm not going to use the calculator. I'm just going to rely on the definition. So like problem 1. For instance, I got log base 2 of 64, right? So let me write it out like this. Y is equal to log base 2 of 64. Okay, just a reminder. According to our definition a moment ago, we said y equal to log base a of x. That means that a to the y is equal to x. So I'm going to rewrite this guy in terms of that definition we have here. Okay, so this means that 2 to the y is equal to 64. You see that? And now I got to just figure out what is this y. All right, well, how could I figure that out? Well, you kind of just think, right? You kind of just think 2 to what power is equal to 64? And these are easy enough that I can just kind of do those in my head. 2, 4, 8, 16, 32, 64. That's 6 times I counted. And I was literally just using my fingers. So it's so embarrassing. Okay, so y is equal to, y is going to be equal to 6 then. Because, why? Because 2 to the 6th equals 64, right? 2, 4, 8, 16, 32, 64. Yeah, so I wanted to double check myself. So y is equal to 6. And what is y though? Y is log base 2 of 64, right? So 6 is really our answer. Not the y equals. I just introduced y as a kind of a placeholder. So I guess to complete the question, I should say log base 2 of 64 equals to 6. That is your answer, number 1. Okay, I'm going to speed things up here a little bit because after doing that first one, you kind of get the idea, right? So let's go with the minimum amount of work that you should probably show. This is number 2. Log base 2 of 16. Oh, it's like even easier. Basically the same question, right? This means that 2 to the y, or you can even actually say it this way, guys. Check this out. You can even say 2 to the log base 2 16. This is what y is, right? This is an alternative notation. Is equal to 16. Well, 2 to the y is equal to 16. 2, 4, 8, 16. 4 times, right? So that means log base 2 of 16 is equal to 4. So the answer is just that. I basically did the same thing I did last time, except I just didn't bother replacing this whole thing with a y. But if you prefer to do that, write this whole thing as y, then please feel free. Okay, number 3. Oh, check this one out. Log base 3 of 1. Well, this is actually a very easy question, and it brings up a general principle. Number 3, log base 3 of 1. Let's rewrite it in exponential form. This means 3 to the thing that we're after, which is the log base 3 of 1, right? Is equal to 1, right? Okay, I know as I'm writing this, I'm kind of feeling like I'm going to confuse you guys by writing it that way. Let's take the extra step and let's write it y equals to that, right? So that's 3 to the y is equal to 1. Well then, what's going to give me 1? It's going to be 0, right? Anything to the 0 power is 1. And this brings up a general principle. Anytime this guy is a 1, then it's going to pop out as 0. Because the only thing that's going to give me a 1, if my base is anything except 1, and it cannot be 1 because we said earlier he's not allowed to be 1. The only thing is possible is 0. So there it is. Number 3, done. Okay, moving right along. Okay, number 4. Oops, sorry. Number 4. Log base 5 of 125. So let's see. Y is equal to log base 5 of 125. That means 5 to the y is equal to 125. That's 5, 25, and then 25 times 5 is 125. So y is equal to 3. And so 3 is your answer here. Yeah. Log base 5 of 125 equals to 3. Didn't write the parentheses earlier. Sorry. See, these are not so bad, right? Not so bad. Just basically applying the definition, filling in what's that missing exponent. That missing exponent is the logarithm. Okay, 5. Okay, log of 1. Remember what we said earlier? Oh, sorry. In this question, it's going to be 0, right? We already know it's going to be 0. But because anything, if it's going to give me 1, then the exponent must be 0. So there it is. But let me also make a side comment. What does this mean? Do you remember? It actually means log base 10 of 1 is equal to 0. So if you wanted to show extra work, now I wouldn't require it for this particular one. That would be enough for this particular question. But if you wanted to show work, you could say y of log base 10 equals to 1. Because that's what this is. Log base 10 of 1, sorry, is equal to 0. Because that's what this is, right? This is the common log. If it doesn't say explicitly, we're assuming the base is 10. So that means 10 to the y is equal to 1. And y, again, is equal to 0, but we already knew that. Okay, 6, 7, 8, 3 more. So here's 6. Oh, ln e, nice question, nice question. What does ln mean, you guys remember? This is, ln means the base is e. So it's e to the e. Another general principle here we're seeing here. If I have the same base and the same number, the base is equal to the inside of these parentheses, then the answer is always going to be 1. It's just saying it's itself, right? How does this translate? If I say y is equal to this, it's saying e to the y is equal to e. But what's going to give me back itself? That's if the exponent is just 1. So y is equal to 1. So you can also say, completing the original statement, the natural log of e is just 1. Or if you like it better, log base e of e is 1. It's just different notations to say the same thing. Yeah, there it is. Okay, 2 more, and then we're gonna cut this video off. Okay, number 7. Okay, number 7. Another general principle here. This is not a possible. The undefined. And why is it undefined? Because 0, remember, 0 is not in the domain. Remember our domain? Our domain was from 0 to infinity, but not inclusive. You see how this is a open parentheses here? That means we're not including 0 as a possibility. Why is that? Well, let's take a moment here to just examine this a little bit. Why? Let's say y equals to ln of 0, right? That means, what does that mean? Well, ln means log base e of 0, right? Okay, so that's saying that e to the y is equal to 0, but what could I possibly take? What possible exponent could I take that would give me 0? There's nothing. You could get very close to 0 by choosing like a big negative number, but you would never actually reach 0. And that's the mathematician's perspective, because like if you ask someone like more practical, like an engineer, they might say you can get arbitrarily close to 0, so let's just determine some reasonable closeness within like let's say a millionth, and we'll say that's good enough. But I don't know. Mathematicians don't think that way. We're pretty impractical a lot of times. Okay, ln e to the 5. Here we have another general principle here, guys. Watch this. What is ln? It's log base e, right? Okay, this is actually going to pop out in the rules next time, so it's not really that important here. But check this out, look. You see how this e matches that e, right? And so just think about what this means. If I say this is okay, this is y equal to that. That means e to the y is equal to e to the 5. So that means this y must have been 5. Right? So what's the general principle? If you have the same base here and you have the same base to some power, then the logarithm is just that power. But yeah, I mean, that's not something you really have to memorize, because you know why? Because you're gonna remember some rules of logarithms in the next section, and then this will be easy to deal with from there. So anyways, y equal to 5 in this case, that means the original question, ln of e to the 5 is equal to 5. So there's your answer, and we're done. Okay, see you in the next one.